Okay, now we move on to stopping site distance and Sag vertical curve design. So for the difference between, there's a difference of course between Sag vertical curve design and the crest vertical curve design. So for the Sag vertical curve design, it differs from the crest vertical curve design such that the site distance is governed by nighttime condition. So in the design for Sag vertical curve, it is actually governed. One of the factor is the nighttime condition because during daylight or during daytime, sight distance on a sag vertical curve is unrestricted. So the critical concern for sag vertical curve design is actually the length of the roadway that is illuminated by the vehicle headlight, which is a function of the height of the headlight above the roadway and the inclined angle of the headlight beam. So that is relative to the horizontal plane of the car. So we have here an illustration for our sag vertical curve. So this is the stopping site distance illustration for the stopping site distance consideration for Sag vertical curve. So for this one, we have our S, capital S, which is the site distance that is from the driver's eye. And our H, of course, is the height of the headlight for our car. Our beta, that is the inclined angle of headlight beam in degrees. Our L is the length of the curve. And of course, this is our sag vertical curve. We have our L, which is the distance this is measured from the initial, from PVC towards PVT. And of course, we have our PVI. Our PVI is the intersection between the tangent of the initial and our final grade. So we have to take note that for us to determine the minimum length of the curve for a required site distance, the properties of a parabola for an equal tangent curve can be used to show that we have two cases. For S is less than L, we have the minimum length of the curve, which is AS squared all over 200 times H plus S tangent beta. And when S is greater than L, we have L sub M, which is equivalent to 2S minus 200 quantity H plus S tangent beta all over A. So we have to take note, of course, that our L sub M is the minimum length of the vertical curve. So in this case, we are talking about our sag vertical curve, and our A is the absolute value of the difference in grade. So that is G1 minus G2. So based on the for AASH2, there's a recommendation or a design guideline for in AASH2 for the site distance required to provide adequate stopping site distance. According to AASH2, based on their design guidelines, they make use of the headlight height of 2.0 feet and an upward angle of 1 degree. So if we try to substitute this design guidelines of the AASH2 to our previous equation and we refer our S be equivalent to SSD as one of the crest vertical curve case, and again ignoring the relatively small distance from the driver's eye position to the front of the vehicle, the previous formula can be written now in this manner. So we have for SSD, which has less than L, so we have L sub M, which is equivalent to A times SSD squared all over 400 plus 3.5 times SSD. And for SSD greater than L, our L sub M is equivalent to 2 times SSD minus 400 plus 3.5 times SSD all over A. We have to take note that our SSD is the stopping site distance. And our A, of course, is the absolute value in difference between our initial grade and the final grade. So for as one of the case in our crest vertical curve, we have also the value for K, which can be computed by assuming that our L is greater than SSD. So it gives us a linear relationship between L sub M and A. So therefore, if we, for the sag vertical curve for L sub M, which is equal to K times A, so we can have our K value, which is equivalent to SSD squared all over 400 plus 3.5 SSD. So our K, we have to take note that is the horizontal horizontal distance that is required to effect a 1% change in the slope. So that is a horizontal distance that is required to effect a 1% change in the slope. So for our K values corresponding to the design speed, SSD are presented in our tabulation, that is presented in tabulation, or that is presented in table 3.3. So same with the case for the crest vertical curve, we have some caution should be exercised in using this table 3.3 because the assumption that G is equal to 0 in the determination for SSD is being used. We have also assumed that L is greater than SSD, which is safe, conservative assumption. So same as with the case of the crest vertical curve. And we have to take note that the smallest allowable curve length for sag vertical curve are the same as those for the crest vertical curves. Okay, the first problem is an equal tangent sag vertical curve has an initial grade of negative 2.5%. It is known that the final grade is positive and that the low point is at elevation 270 feet and station 141 plus 00. The PVT of the curve is at elevation 274 feet and the design speed of the curve is 35 miles per hour. So determine the station and elevation of the PVC and PVI. So this is a sag curve. So for this one, so if you're going to have this sag, if you're going to have the if you're going to have the sag curve, so you can be drawn into this form in this manner. So this can be PVC. So we'll have your PVT. So we are given with our initial grade, which is G1, negative 2.5%. And the elevation at the low point, so probably this will be the low point. Elevation is 270 feet. And of course, the station is 141 plus 00. So the curve is at elevation. The PVT, the elevation of PVT is at 274 feet. And of course, the curve has a design speed of 35 miles per hour. We are after to solve for the station and elevation of PVC and PVI. So these are the station and elevation of PVC and PVI. So those are unknown. So to start with, you have to take note that from this table, this is the design control for sag vertical curve based on stopping side distance. So for this one, from the table, for the design speed of 35 miles per hour, so we have the value for K, which is 49. So if we're going to have this, we can compute now for the distance of the lowest point from PVC. So what will be the distance of this lowest point from PVC? This is X H of L. So we have the formula for that, which is for that one to compute for the value for that distance for the lowest point, which is having an elevation of, this is an elevation for the lowest point is 270 feet, station at 141 plus 00. So this one is our X, the distance of the lowest point from PVC. This can be called as XHL. So therefore, if we're going to have here X of HL, the formula, we are given now with our K, which is equivalent to 49 based on table 3.3 because K is 49 for design speed of 35 miles per hour. So from this formula, we can compute now for the distance of this lowest point towards PVC. So this is K times G sub 1. So we have the value, which is 49 times our G sub 1, which has 2.5. So it gives us 122.5 feet. Since we have now the value for the distance, our x is the distance from the lowest point, and we have now the elevation of the lowest point. So therefore, we can compute the elevation of PVC. So elevation of PVC. So the formula that you will be using is the parabolic equation, y is equal to ax squared plus bx plus c. We have now the value for y, which has the elevation at any point on the curve. So for this one, we're referring to the elevation of the lowest point, which is equivalent to 270. Our x here is the distance of the lowest point. Since we will be using the lowest point on the curve. So we have now the elevation of the curve, we have the distance of the lowest point from PVC, and our C is the unknown, which is our elevation of PVC. C refers to the elevation of PVC. So therefore, our A here, from the equation G sub 2 minus G sub 1 all over 2L. So we can have G sub 2, which is actually equivalent to, this is, you have to take note that G sub 2 minus G sub 1, this is also equivalent to the absolute value of G sub 1 minus G sub 2. And actually, this is equal to our A. And if we try to make use of that, we can have our A. We can have this equation. A is equal to G sub 2 minus G sub 1 all over 2L, or G sub 2 minus G sub 1 is actually equivalent to A. So this is, we are going to divide this by 100 to make, this is over 100 to make sure that the units are inconsistent with the denominator since L is in feet. So this will be all over our 2L. Our L here actually is, L is equal to K times A. So this will be K times A. So therefore, if we try to simplify this one, we can have the value of 0.01. We can eliminate some of the terms over to K. So therefore, this will be equivalent to 0.01 all over 2 times 49, and this will be equivalent to 0.00012. So we have now the value for our A. And of course, our B is actually equal to G sub 1, and this is equal to negative 2.5. So we have now the value for our B. So therefore, if we are going to substitute now to this equation so that we can solve for our elevation. So we can have our elevation of PVC from y is equal to ax squared plus b plus c. So c is the elevation of PVC. Our point, the lowest point that we are referring is 270. This is the elevation, equal to 0.00. Substitute the values. 102 times 122.5 squared. This is the value for x, the distance of the lowest point towards from PVC. Then this is plus negative 0.025, which is our B, times 122.5 plus C. So if we try to simplify, our C here is 271.53. So this is now the elevation of PVC. So from here, so since we have now the station of the lowest point, which is 141, and the distance from PVC is to the lowest point is 122.5, so we can have now the station. So the station at low point, station is at 141 plus 00, and its distance from PVC is 122.5 feet. So therefore, to have the station of PVC, this will be equivalent to 141